Here we are, Joseph. We're about to do a large building test on a building at Melbourne University, the Cultural and Arts Building. I think a lot of people ask questions what an air tightness test is, and at the end of the day, a lot of people understand air changes an hour at an elevated pressure of 50 Pascal, which is roughly 32 km/h winds. But today we're testing for a permeability rate. What does that mean?
An air tightness test is a procedure where we using the fans to pump air into a building to elevate the building into a standard pressure. Typically is 50 Pascal. If you are in the US, you may use a different standard that need to elevate to a 75 Pascal. In this process, the fan is connected to some other device, which is the manometer, and it calculates how much air, the volume of air is moving through each fan. So the process, practically what we are doing is measuring the volume of air that we need to put in the building to get it to the standard pressure level.
And a permeability rate means that per every square metre of building envelope, that's the ground floor of the building, all of the facades and the roof, how much each square metre is leaking per hour. And what that enables us to do is then compare apples with apples of other buildings on how leaky they are.
That's correct, because if we just tell the design team, the consultants, how much air we need to put in to elevate the pressure, it's not that friendly for them to do their calculation and sizing their mechanical system, or for the builder to evaluate how well they built. That's why typically we have two types of method to present the result. One is what John just said, is the permeability rate, which is aimed to compare the build quality between buildings, because it's normalized to the surface area of each building. So it doesn't matter whether you are building a large or small building, the number are comparable for each meter square of surface area. However, on the other hand, the air change per hour, which is used the volume of air we pump in divided by the volume of the building. What it is useful is for the mechanical designer, because they are typically designing with how many times they need to bring in the outside air for fresh air, or how many times they need to recirculate the conditioned air to provide a comfortable environment. That's why it's more instinctively understood by the mechanical consultant, the number of air change per hour.
So now it also depends on, from an energy efficiency perspective in air tightness, it depends on where these holes are and whether they feed themselves. Now wind and stack effect, especially stack effect, when you've got holes at the top of the building and the bottom of the building, these holes complement each other and can hemorrhage significant amount of air, can't they?
Yes, and that is exactly the reason why it's very difficult, if not impossible, to try to quantify an energy saving by reducing the air leakage level, because exactly as John just described, the location of the hole and the characteristic, the size of the holes make a lot of difference in terms of the direct energy loss to the outside. For example, if you got a lot, thousands of tiny holes, when the air around the building is still, the actual energy loss may be very small, because it doesn't have the drive to push the air through those small holes. But if you got bigger holes, particularly if they are at high level near the ceiling, then in winter you lose the majority of your heating through those holes.
Your building just becomes a big chimney.
Yep.
So we've set up a pretty big test here. There's 7 blower door fans, which are scattered at the top of the building and the bottom of the building. What's the importance of wind, and also how high you can get the pressure in a building?
Well, it all depends on the how airtight the building is to begin with. And the wind can have a detrimental effect because it can be directly competing with our fan on one hand. On the other hand, it may create an uneven drag of air in different portions of the building. Usually wind got higher effect near the roof level. So we need to balance out the effect of wind with our fan, and it makes the whole process a lot more difficult, and it's harder to get reliable and repeatable results.
Because when you've got problems, I mean, with such a large building, I mean, this is quite a complex building and it's a very beautiful building, but you've got to work out where things might be causing issues with the testing, whether it be ductwork, whether it be just something incomplete in the building, or whether it's just doors that aren't latched properly are opening up. And then looking around this whole building to find these issues just takes time.
Well, that is already the next step where we start to do troubleshooting to find what is the issue causing the problem that we collect. But even when we're just doing the test, it is a lot more involved to try to run fans at different locations at different speed to try to compensate the effect of wind.
Currently, the GBCA or Green Star have got a requirement for testing a building to a permeability rate of 20, which is 20 metres cubed per metre square, 50 pascals. In a lot of circumstances, it's very difficult to test a building to that leakage rate because of interconnectivity of the building to these openings that might be to the outside. What's the easiest way to get out of having cheaper testing and easier tests on these buildings?
Well, it all comes back to the air tightness level of the building. If the builder can build the building tighter, it is better for the client, more energy efficient, better comfort, cheaper testing, easier for us to conduct the test as well. So it's a win for everyone to build tighter.